Okay, physics review, chapter 3. We're looking at acceleration for this chapter, and we're looking at acceleration across the horizontal and the vertical. Okay, so we're going to look at the distance. Look at your objectives. That'll kind of tell you where we're going with it. So distance and displacement, scalar and vector. Okay, understanding how a distance time graph is formed, the significance of the slope, that would be kind of important. And then understanding the rate of motion. Okay, so when I look at displacement and distance, they're two different things. Displacement is how far is it from point A to point B in a straight line. That is your displacement. Your distance, on the other hand, can be any range that you go, any length that you're going through. So can the distance be the same as a displacement? Yes. Okay, but more often than not, the distance is not the same as displacement. Okay, I gotta go fast here. Scalar and vector. Scalar gives you one piece of information, 15 kilometers, that's a distance. 4 meters per second, that's a velocity. Scalar tells you two pieces of information, and that typically would be a direction. So 15 kilometers north, 4 meters per second east. Notice I put in a compass points there because that's telling me the direction, okay? Which is what all of us need in our lives. We need direction. Can you have a negative distance and displacement? Absolutely. Does the negative mean a bad thing? No, it's the direction that you're going in. So if I'm going this way, it's positive. On the other hand, if I'm going this way, it's negative. Moving on. You should be able to recognize a graph like this, distance versus time. You should be able to tell me what's happening with these lines. So in other words, if you're going up like this, guess what? You're speeding up, you're increasing. When you are here, are you moving at all? No, because the distance isn't changing. Time moves forward, okay? If you're going down this way, okay, that means you're going down, down, down. You're going backwards, son. You're going backwards, okay? Because you're going back over the distance. Remember, time keeps moving forward. So you should be able to look at a graph and be able to tell me about that, okay? The other thing, we can talk about position time graphs. Here, you should be able to recognize a distance time graph or a position time graph. You should be able to tell me that the slope should be distance over time, which happens to be velocity. So the slope of a distance time graph is in fact velocity. You need to know that, okay? So here are some examples here. You should be familiar with this. You should be, again, look at a graph and be able to tell me what's happening. Okay, formulas. Here we go. You are so getting the formulas, okay? So average velocity is our distance divided by the change in time, or the absolute value of delta x over delta t. You'd say, but wait, what is the delta x? You could look at that as position, okay? So we did some examples in class. Hopefully you were paying attention and you actually worked the examples on your notes, because that would be a useful thing to have, okay? Moving on here, okay. We're not going to worry about instantaneous speed. Do not worry about this. So here we go. Here's our formula number 2, looking at our average velocity. Again, distance divided by time. You'd say, but what's the difference between that and that? Not really a lot of difference. You could sit there and look at position and displacement, okay? I would sit there and I would look upon that like distance. Even though I say S is distance, the D here, you could look at that as distance, the overall displacement. Okay, so we went through some examples for that. Then we went to acceleration. So here's the thing about acceleration. Acceleration, this is where you get the meters per second per second. In other words, in 1 second, how much did your velocity change? If it's negative, it's decelerating. If it's a positive number, it's accelerating. That's the difference. Okay? So this is for a constant acceleration, an average acceleration, delta v divided by delta t. Remember that delta means change. What are you ending with? What did you start with? So what you end with minus what you start with. Okay? Which shows us right here for this. Okay? Now when we look at V2 and V1, think about the start and the end. Could V1 be 0? Yeah, because your object could take off from a complete stop, right? Could V2 be 0? Yes, because you could come to a stop. Okay? Can T1 be 0? Yes. Can T2 be 0? No. It was an awesomely successful movie back in the early 1990s. You can't have T2 be 0, guys. You can't. All right, again, look at the objectives, because that's going to give you a clue of where are we headed. I've got to wind down this chapter. I'm running out of time. Okay, so here's some examples working with the acceleration. Okay, here's our first equation of motion. V2 equals V1 plus acceleration times delta t. Now keep in mind, this is just saying the same thing as this. That's exactly what it's saying. It's just a little bit more fleshed out. That is the difference. Okay, I gotta go back here. Oops. So, with that we did, so here is our second equation of motion. Okay, and again, it's fleshing it out. Now, what's the difference between the x2 and the x1 and the d? The x2 and x1 talk about position. My car starts at 100 meters. I'm going to 500 meters. That's an x1, 100 meters, x2, 500 meters. The d represents x2 minus x1. So 500 meters minus 100, my d is 400. It's still the same formula, it's just expressed a little bit differently. Now, could your initial velocity and your initial position be 0? Yeah. So then x2 is equal to 1/2 acceleration times the change in time. You can do that. Okay? Homework problems? Yeah, due on the day of the test, but here's something to think about. I might be using some of those, change them a little bit, and put that on the test. So there would actually be an advantage to doing the homework. Yeah, that's it. All right, let's move on here. So we talked about the second equation of motion. We went through that. Third equation of motion, here's another one. When do we use this one? That's when you're not given the time. Okay, I don't have the time. What am I going to do? This is it right here. Now again, the x2 and x1, again, it's position 1, position 2, like in the previous problem, and then here is our displacement. Okay, so we have those two formulas there. Okay, so again, I made examples where the numbers are small, and you can easily work that out. Okay, and if you paid attention in class, this shouldn't be too bad. All right, let's move on here. So third equation of motion, again, this is using another example here, and then we're coming down, we're winding down the review here. Free falling now, free falling now. Okay, so this is 9.8 meters per second squared. If it's negative, that tells us it's going up. The object is being thrown straight up, not at an angle, straight up. Okay, same thing if the object falls straight down. All right, that's a key thing. So if it's negative 9.8, that means it's decelerating, which makes sense because what goes up must come down. All right, so free falling happens under two conditions. The acceleration is under the gravity alone, and air resistance is negligible. Sadly, with our little experiment with the golf balls, we do have air resistance. We cannot escape that. All right. So the really cool part about G is you can use all those other equations and substitute the acceleration due to gravity on that. But again, this is only for up and down motion, not this motion, up and down. Not this, up and down motion only. That's when you're going to use the G. All right? So again, we worked with some examples there. Woo! Okay, lots of formulas. How will I know? Okay, so read the problem through. Number 2, I think this is where a lot of you guys are struggling with this. You need to identify all the variables. Because honestly, I know you guys can pick the formulas and you can plug in the numbers and you can work the calculator. Wow, a senior at USC can do that, okay? But in this case here, this is it. If you can't identify the variables in the problem, you're not going to solve the problem, okay? You've got to be able to identify the variables. That's the thing. Solving the problem is the last thing. Okay, guys, I'm going to have to stop here. Okay, that's the end of the review for Physics Chapter 3. I hope that you benefited from it. And, well, I'll see you all the next time.